Just going to start recording. Thank you everyone for those of us in Australia being here bright and early to attend these Sensorimotor Control Down Under meetings. I'd like to start by acknowledging the traditional owners of the lands on which we meet today. I'd like to pay my respects to the elders past, present, and emerging. And today we have the pleasure of hosting Jonathan Tsay. Jonathan is an assistant professor at the Carnegie Mellon University. Um, and he's the director of the Physical Intelligence Lab, Phi Lab. And the lab's mission is to understand how humans learn movements and master, things like making coffee and parallel park. They use methods from computational modeling, psychophysics, and testing patients in order to try to understand the principles of learning and memory and also inform rehab and human performance. So JT has a background in theoretical mathematics from Northwestern University and physical rehab also from Northwestern. And then I think, completed a PhD with Rich Ivory at UC Berkeley. And yeah, we're very happy to welcome Jonathan to present to us today. So over to you.
Wonderful. All right, let me share my screen. Thank you, Leon, for the kind invitation. And let me just make sure I share my sound. I have a video.
Mhm.
So it's a pleasure to be with all of you here today. And today I'll be talking about the behavioral, neuropsychological, and computational perspectives of motor learning. And I love this to be a discussion, so please chime in anytime and interrupt me. And Leon, just let me know if time is running out. And so just to add a little bit more context of where I'm coming from. So I was raised in Taiwan and actually in the Silicon Valley area of Taiwan, which is becoming a key area. I didn't really appreciate the significance of it until maybe now. And this is where all the chips are built in Apple and everything like that, TSMC. But being in that environment, I really developed an early interest in math and science, just being in that kind of engineering environment. But at the same time, I just spent my youth really playing a lot of basketball. So when I went to Northwestern University, I thought, okay, what should I dive into? And I thought math would be a good choice because it would serve as a common language for whatever science I decided to pursue. I was pretty undecided at the time. But during my third year of uni, I had to make a decision about what I want to do. And I thought, I still love basketball. I love math. I'm still not sure what type of science I liked. And I thought, what a great way to bridge all three areas by pursuing a physical therapy degree, or maybe some of you call physiotherapy. It's a great combination of science, math, and an ability to contribute to society. So I continued my education at Northwestern to pursue physical therapy, and that was a 3-year program. And it was really during that time where I was exposed to physical therapists in the ICU, physical therapists, in the MBA courts. That's was the dream at the time. But really, what struck my attention was being a physical therapist in the neurological rehabilitation clinic. It was there when I was treating people with spinal cord injury, stroke, Parkinson's disease, and I really made a important realization for myself then. And it was in order to better treat people with brain injuries, we needed a better understanding about how the brain worked to control movement. And so that realization is what brought me back to school and to pursue to pursue a degree in psychology, especially a PhD focused on how humans acquire, adapt, and retain motor skills. And so my PhD really focused on motor learning. And since then, when I launched the Physical Intelligence Lab last year, that's been our central focus to understand how do humans acquire, adapt, and retain motor skills. And along this theme, we've been answering questions such as how do different practice schedules impact motor skill acquisition? Should we practice one thing at a time, or should we practice multiple things at once? We've also asked how's motor learning disrupted by rapid changes in the environment? For example, if a sudden gust of wind blows your basketball, how do you quickly adapt to this disruption? We've asked how does sensory uncertainty modulate motor learning? For example, visual uncertainty for example, proprioceptive uncertainty. How do those aspects of sensory input affect performance? We've also asked, what is the optimal time to provide feedback during motor learning? Is it right when you move, after you move, or throughout movement? Let me just put this headphone on. And we've also asked, how does stroke impact motor learning? Sorry, give me 1 second. Uh, Leon, can you still hear me? Okay, perfect, perfect. Okay. And we also have asked, how does stroke impact motor learning? For example, if you have left hemispheric stroke, right hemispheric stroke, how does that affect the way you learn? But today I'm going to focus on what I see as my three main contributions thus far. And the first is the computational mechanisms of motor learning. What are the basic mechanisms that help us learn new movements? I'm also going to share some work on the cerebellum's role in coordinating action and cognition. So we always think about the cerebellum as something that helps us coordinate movement, but more recent work is about how the cerebellum helps us coordinate our thoughts. So I want to share some theories about that. And lastly, I want to share some more recent work on leveraging online data to study motor learning at scale. And we're going to cover methods such as computational modeling, patient work, and also large data machine learning. So let's dive in on the computational mechanisms of motor learning. So this crowd is very familiar, motor learning, especially the concept of motor adaptation being the process of our ability to reduce motor errors. And I love this video that I'm going to play because it illustrates motor adaptation happening in real life. Yeah, I'm not sure if you guys could hear the volume, but it's awesome. But yeah, it's a video I love for a variety of reasons. Not only does it show like how this kid is quickly reducing his motor errors through adaptation, but also it illustrates that motor adaptation is supported by multiple learning processes. One process just helps this kid implicitly through trial and error reduce his motor errors over time. But on the other hand, explicit strategies through instructions from others, through strategies that other people provide to jump higher and aim for this point, help us quickly and flexibly reduce motor errors as well. So when I started my PhD, became really interested in the mechanisms that support implicit adaptation. And there are many ways to look at this process of implicit adaptation. At the time when I joined the lab, one of our favorites was the clamp feedback task. I know some of you are familiar with this task and have used it yourself in your research. So in this task, participants are in this dark room. They're making reaching movements to a target. They don't see their hand, but they see this cursor that represents their hand on the screen. And during these baseline trials, when they're simply asked to reach towards the target, they can do so without any issue. And you can see that represented as a hand angle of 0 across time. So during the baseline phase, people are reaching to the target. But critically, when we introduce a motor error artificially by rotating this cursor to the left by, let's say, 15 degrees, and we actually ask people to ignore this cursor, reach straight to the target. Don't do anything else, just reach straight to the target. And no matter where they reach, this cursor will always be moving 15 degrees to the left, always having this 15 degree of visual error. But despite these instructions to always reach to the target, ignore this visual cursor, participants can't help themselves but start to drift further and further away from the target, eventually hitting an asymptote around 20 degrees. And people, if you ask people, are they aware that they changed directions of their movement? They would say no. If you ask people where they're reaching, they would say, I'm reaching straight to the target. So this is a very implicit process. And we think through this task, we've isolated a more implicit process of motor adaptation. So I want to pause here in case anyone had any questions about the paradigm, because I'll be showing this several times. Good. Okay. So what are the mechanisms that people have thought in the literature that drove learning? a key model in the field, what I call the visual centric model, or many people call the state space model, presupposes that learning is driven by a visual error, a mismatch between the visual cursor and the target. And eventually, learning hits an asymptote because learning that's pushing you away from the target is somehow balanced by forgetting a passive decay that's pushing you back towards the target. And that's why you have this process of implicit adaptation that's driven by a balance between learning and forgetting. And we've employed these state-space models through our research for a long time. But as a physical therapist coming in to do a PhD, I was a bit unsatisfied with this model because I knew that vision was not the only sense that helped us guide where we move. We also use proprioception to guide our movements. So I asked a very simple question. I asked, where is the hand perceived during adaptation? We always assumed it to be at the target. You know, we asked people to aim towards the target, but where, in fact, do people think they moved? So in this experiment, we did something very simple. After every movement, we introduced a wheel of numbers and we said, hey, where do you think you moved? If you think you reached the target, say 0. If you think you reached to, somewhere to the left, say a negative number. If you think you moved to the right, say a positive number. So during baseline, people are reporting that they reached the target, which is exactly where they moved. But critically, when we introduced this visual error, this error clamp of 15 degrees to the left, participants actually report that they feel like their hand has been biased slightly on average towards the direction of the visual cursor. So they report something like -1, represented by this line here. And over time, as people adapted, their hands started to drift away from the target, but they started to report that their hand has been somehow realigned back to the target, and in fact, overshooting the target a little bit. So this unique trajectory, so this is actually what it looks like. The participant is moving away, they're implicitly adapting, but their perceived hand position is slowly realigning back to the target, initially biased by the visual cursor. So this unique trajectory, initially we didn't make a lot of inferences based on this trajectory because it's quite subtle. But over time, as we were thinking about this trajectory, this initial bias towards the visual cursor and gradual realignment towards the target inspired a new way of thinking about adaptation. Instead of learning being driven by visual error and hitting some asymptote when learning is balanced by forgetting, we thought maybe learning is driven by this perceptual error, this this error between where you perceive your hand to be or perceive your movement to be and the target, which is the goal to reach to the target. And learning is simply hitting an asymptote when you feel like your hand has been realigned back to the target. And so we called this model PRIMO, or proprioceptive realignment model, or perceptual realignment model. So we called this model PRIMO. And this model is useful. So before that, let me spell out a bit how this model works to give you some intuition about how these signals interact. So PRIMO suggests that there's multiple inputs, proprioception of the hand, visual sensory signals from the visual cursor, and also this often neglected idea of this belief that you reach to the target because you aim to the target. And so these three signals form one unified sense of perceived hand position, and that results in a misalignment, this error signal, and therefore that drives adaptation towards the right to reduce this error. So specifically, and the model suggests that vision and proprioception both get first biased towards this belief that the hand is at the target, forming what we call the integrated hand and integrated cursor positions. And then, based on a lot of literature in psychophysics, the hand proprioception and vision recalibrate one another. And Eugene has done some work on this, where proprioception gets biased by vision, and then vision gets biased by proprioception. So we call this the proprioceptive shift and the visual shift. And it was initially quite surprising to me that vision can get biased by proprioception because we always think of vision as a very immutable sense. But in fact, there is this subtle visual shift that also occurs. And so therefore, the hand is perceived to be misaligned to the target, and therefore that results in a perceptual error, and that's what drives implicit adaptation. So that's the model we formalized. And why is this model useful? Well, one reason it's useful because Primo can account for some unexplained phenomenon in the motor learning literature. So not only does it explain that we adapt, but also this perceived hand position that initially gets biased towards the cursor and it gradually realigns back to the target. The state-space model, the visual centric model, does not make this prediction. It's pretty moot on where you think your hand is. But we built that model inspired by that finding, so that's not very surprising. We Another true test of the model is what it predicts about where people asymptote. Why do people saturate at 20 degrees or 25 degrees or 30 degrees? And this model suggests that the asymptote of learning depends on your proprioceptive noise. It depends on how much you get biased by the visual cursor. So if you get biased more towards the visual cursor, you would adapt more. If you have more noisy proprioception, you would also adapt more. And it also has this factor of prediction noise. How much do you believe that your hand reaches to the target? So in the next few slides, I'm going to show you some evidence that is convergent with Primo and this idea that the asymptote depends on these three factors. So the first notion is proprioceptive noise. So the way we measure proprioceptive noise is by asking people by passively moving their hand using the kin arm, or when I was a PhD student, we moved it with the experimenter. We called it the human robot. I would move the participant's hand to an unknown location, and they would indicate using their opposite hand where they think their hand is and this was before any adaptation. So indeed, participants who showed greater noise, which is the standard deviation of their reports, were also the individuals that adapted more. So this is some correlational evidence that if you have noisier proprioception, you weight vision more, and therefore you require a greater change in hand position to realign the perceived hand position back to the target. And quite encouraging to us recently, Denise Enrique's lab found the same correlation. She went back to her data across like 10 years or something like that. And they also looked at passive localizations, so this proprioceptive noise, and you can see that it correlates with implicit adaptation. So that was encouraging, but you might be thinking, okay, this is correlation, not causation, and these might be bad participants and these might be good participants, so on and so forth. So when I arrived at Carnegie Mellon, I really tried to focus on seeing if we can find some causal evidence for this correlate for the impact of proprioceptive noise on the asymptote. So to do this, it's hard to manipulate proprioception, but one really unique way of doing so is through direct spinal cord stimulation. So these are very rare patients who have a stroke, and they've been implanted with spinal cord stimulation. And this is in collaboration with Eric and Elvira at UPitt. And so spinal cord stimulation is helpful to them. It improves their strength and dexterity. But at the same time, it actually adds noise to proprioception because where they're stimulating is along the proprioceptive pathways in the spinal cord. So they measured this using this passive elbow flexion task. So this device is going to flex you upwards or extend you downwards. And your goal as the participant is just to tell me if you were flexed or extended and as quickly as possible. So you can see that in this one participant, when the stimulation was off, they quickly detected that their arm was flexed or extended like 2 degrees. But when the stimulation was on, and note that this improves their strength and dexterity, right? So this is good for them. But inadvertently, their detection angle is almost doubled. So it takes them a little bit longer for them to sense that their elbow has been flexed. So in other words, proprioceptive noise has been slightly increased. And so based on Primo, we would predict that these patients would also show enhanced implicit adaptation. And so that's indeed what we found in this one participant. This participant was a super adapter. Stimulation off, they adapted 60 degrees, like they're reaching way off. But turn on the stimulation, they went even further to like almost like 90 degrees. And that was just one participant. So we try to replicate that in another participant. So here again, proprioceptive noise has increased in this another participant. And again, this is a more reasonable level of adaptation around 0 to 15 degrees. And you can see that stimulation on, there's more adaptation compared to stimulation off. So I know these are case studies, but it is suggesting that proprioceptive noise may have a causal role in driving implicit adaptation. But that was just spinal cord proprioceptive pathways. We thought, why don't we try the brain, where proprioception is processed? And so in the literature, especially from David Ostrey's group and Hannah Block's group, continuous theta burst stimulation to S1 seems to enhance proprioceptive uncertainty, seems to kind of basically blast that area and add uncertainty. So this is some of the data from David Oster's group. If you do S1 stimulation, you increase proprioceptive uncertainty based on a two alternative four choice task of where your hand is. But sham stimulation to the vertex has no effect. So it seems like it's a manipulation of proprioception on the cortical level. So again, we would predict that implicit adaptation would be enhanced if we provided CTBS. And so, in collaboration with Matthias from Germany, we indeed see some pilot data that S1 stimulation compared to sham does enhance implicit adaptation. So, again, this provides some converging evidence that maybe proprioception does have a causal impact on implicit adaptation. Another way to test this, although a bit indirect, but it has some clinical implications, is in aging. So we have this finding using an online sample and an in-person sample that older adults adapt more than younger adults. And this is quite surprising to us because the literature was a bit mixed on this topic. But if you do the clamp feedback task, you actually see older adults to be enhanced compared to younger adults. And it's not just this online experiment, this in-person experiment, we recently replicated this. So is this due to them having greater proprioceptive noise? So, one other finding recently was that we try to do this not just on a binary young and old, we try to do this more continuously. And you can appreciate this age-related enhancement over time, over decades. And so there's this nonlinearity that we're still trying to explore, and maybe this is the time course in which proprioception decays as well. So in our in-person study, we also had an opportunity to measure proprioceptive noise, and we predicted that older group would show a worse proprioception. And so that's indeed what we found. Older adults show greater proprioceptive noise compared to younger adults. And that might be the reason for their enhanced implicit adaptation. So this finding actually motivated us to go back to the literature, some of your studies, the studies in the literature to see whether this enhancement is just this weird thing about clamp feedback tasks, or is it like a general phenomenon we see in adaptation. And so when we looked in the literature and we honed in on the after effects, the measure for as a proxy of implicit adaptation, we actually saw a pattern that revealed implicit adaptation in older adults. And not surprisingly, perhaps explicit strategies are reduced when you look at the late adaptation phase. So this combined is providing some evidence, although a bit indirect, using an aging sample that greater proprioceptive noise may be again related to greater adaptation. So proprioceptive noise is not just the only factor that we think is related to adaptation or this asymptote. Primo also suggests that the amount your proprioception gets recalibrated by vision. If it recalibrates more, you have to adapt more to feel like your hand has been realigned back to the target. And that's what we found in the early study in 2021. But again, Denise and Marius put together all their studies from a decade, and again, they see the same relationship. More more proprioceptive recalibration towards the cursor, more implicit adaptation. But what's quite interesting is that proprioception actually saturates for large errors. So if you rotate the visual cursor by 30, 50, 70, the amount your hand position gets recalibrated by vision is pretty constant, around 5 degrees. And this might actually explain why implicit adaptation also seems to saturate for large errors. So in between 7.5 and like 130, in between that, these different cursor rotations, the asymptote of learning seems to be very similar. So these two constructs might be related in this way as well. So proprioceptive shift seems to saturate, implicit adaptation also seems to saturate for larger and larger error sizes.
Can I
One
ask you a
of
question
our,
about that?
oh,
Sorry, Phil.
sorry.
Yeah, I just wanted to ask a question about it. So obviously
Oh, I don't seem to hear you. Wait, give me 1 second. Um,
can you hear me now? I
Sorry, maybe
wonder
I need
if
to put my headphones on. Yeah, let's see.
I think my microphone's on. Can everyone else hear me? Yeah.
Oh,
Got it?
okay, I can hear you now.
You
Yes.
can.
Sorry about
Yeah,
that.
I
Yeah,
can
no,
hear you
sorry.
now.
Just wanted to talk about that point. So obviously the range of values you're talking about there for the two different saturation points is quite different. So do you know what happens at very small visual angles in terms of there. So for
Yeah.
proprioceptive shift, obviously implicit adaptation saturates down to like 5 or 4 or something like that. So do we know what that looks like in the visual error shift?
Yeah, so currently, uh, I don't think there's data on that yet. And I'll be really fascinated because right now the rotation has been abruptly introduced, right? Uh, and and it's always been above 30 usually in Denise's study. So I don't know. I haven't seen a study where they gradually rotated it or they had a 1 degree clamp. I haven't seen that before. But Primo makes a very specific prediction, and that is the proprioceptive shift would be small in the beginning because the visual error is small. But then as the hand moves away, the distance between the hand and the visual cursor also grows, right? As you adapt. And that distance actually generates greater proprioceptive recalibration. So there's a time course to this proprioceptive shift. It starts from 0 and actually goes to 5, or like some level of saturation. And so you might know the Joseph Kim study, like all these small errors, they eventually reach the same asymptote as well. The idea there is that the proprioceptive shift is also going to have a time course from 0 all the way to 5 degrees saturation, and then it's going to drive similar asymptotes even for smaller error sizes.
Gotcha. Thank you.
Yeah, but that's a prediction. I think that would be cool to test it out. One of our newer studies, and if anyone has any ideas about how to test this even further, is how do you manipulate prediction noise? This idea that your hand is at the target. It's a bit hard to manipulate this directly because it's not like a sense, it's like a belief. One idea of how to manipulate this, and sorry, this is a bit overwhelming, but one idea to manipulate this on just like certainty about where your hand is, uh, just like your belief if your hand is at the target, is by manipulating the target itself. So we created a situation where we have a normal target and a situation where you have an arc. And the instructions in both situations is the same. Bisect the target. Okay, just in one case it's a dot, and one case it's an arc. And we assumed that when it's an arc, people are less certain about where they moved without sensory feedback. They just don't see this center, compared to the dot. So Primo would predict that in the case of an arc, you rely less on this belief and you're actually listening more to where your proprioception is, and therefore you adapt less in order to realign your perceived hand position back to the target. And that's actually what we found recently. So indeed, when you have an arc, you adapt less than when you have a dot. And this was the case not just because you have an arc, because we made a condition where it's an arc thing, but here's a dot in the center. And again, you clearly can see, okay, I want to move to this gap. And in this condition, yeah, people still adapt a lot. And when you have this sort of setup, when you're supposed to bisect this empty space, you have no clear reference of where the goal is, you again adapt less. So in conditions where you don't have a clear sense of where the target is, you adapt less because maybe you rely less on this belief that you reach to this clear visual target. This is unpublished work. We're still trying to investigate this. But one interesting, so you can see that the after effects for the conditions where you can clearly see a visual reference that I want to move to it, you adapt more than the cases where you can't really clearly see the visual reference. But interestingly, if you look at the standard deviations of like motor noise during baseline, there's no difference in motor noise. Like people are able to reach and bisect these targets equally well. It's just a matter of how much they use that signal during adaptation. So that might be one manipulation prediction noise. I'll be eager to hear more, but that's a key variable that might factor into implicit adaptation. So to conclude this first part of the talk, Primo provides a holistic view of motor learning, trying to explain different correlations, different time courses of where you perceive your hand to be during adaptation. And not only accounts for vision, but also this belief and also proprioception. So in the next part of the talk, I'll pause here again to see if anyone has any questions. At the same time, I'm going to take off my headphones because it's a bit distracting to hear your own voice. I think I'm going to try that.
I guess, yeah, I do have one question for you, Jonathan. That I think that's fantastic work. I
Sorry,
really,
Raphael.
really like.
I
Yeah,
can't
right.
hear you. Okay, so I guess
Oh, is
maybe I
that
have
right?
to.
Can anyone else
Maybe I
hear me?
have to.
Yeah, yeah, okay.
Okay, I can hear you now. Yes.
Yeah, yeah, okay, fantastic. Hey, that's fantastic work, Jonathan. I really, really enjoy your talk so far, and I'm really keen to hear more about the neural correlates of implicit adaptation because that's typically something I ponder on, and I think that remains sort of ill characterized. But I really like this idea that greater proprioceptive noise could essentially adapt your adaptation capability, right? And as opposed to if I was to extrapolate, it almost seems to be able to enhance motor learning. I can't help but wonder in a real world setting, how would you possibly enhance this proprioceptive noise? How could you leverage this to actually, suppose, say, facilitate limb rehabilitation?
Hmm.
Do you have
Yeah.
any ideas on
So
that? Mm.
yeah, so one caveat here, and I think it's a interesting caveat, is all these learning scenarios that I'm presenting is when the error is visual. Right? When you're learning from a visual error, and a lot of errors in the world are visual. Like you see yourself miss a cup, how do you adapt to it? You're rock climbing, you miss the hold, how do you adapt to it? So a lot of things are visual, and yeah, if you decrease the weight given to proprioception, maybe you are more sensitive to the visual error. That being said, if a lot of you also do force field adaptation, right? If the error signal is proprioceptive in nature, like now you're feeling your hand to be off target, adding proprioceptive noise actually makes the opposite prediction. If there's no vision, that is. If proprioceptive noise uncertainty is greater, you actually adapt slower. And that's actually something we want to just clarify in the literature and try to test this out. So I would say, that's the caveat. Depends on where your error signal is coming from. If it's visual, then yeah, decreasing proprioceptive noise would enhance it. So how would I leverage this in the clinic? I think one thing is for older adults. One thing we're finding, and I think it's convergent with the literature, is they are more visual centered, right? They because of time and aging, proprioceptors do have some decay. Although vision has decayed, is being more and more impaired as well, but at a slower rate. So can we leverage that idea to when we provide them errors to adapt to, instead of dragging their hand and making them feel like where they're moving, maybe we should be a bit more visual to do that, or we can give them some proprioceptive signals to maybe give them a better sense of where they feel like they're moving. So I think this highlights the general principle of aging and how they're weighting these signals. They're very visual reliant compared to proprioceptive reliant. Yeah. Eugene, you had a question?
Yeah, piggybacking on that. So in your equation, the prediction noise, it seems to be a visual based kind of noise according to your manipulation, right? You're playing with the visual target, angle, and dots kind of thing. I'm wondering if you have, I don't know, like some form of, proprioceptive prediction noise would be more apt in this case. And I was thinking along the lines of how do we manipulate this proprioceptive prediction noise in a way? I guess there's some indirect evidence that, when you move to one versus eight targets, there seems to be less adaptation for one versus eight targets. Th- I'm wondering if it could be a related in terms of prediction noise, where, eight targets, you move your hand in a lot of different directions versus in one target, your hand is isolated to a particular direction.
Mhm.
And yeah, I'm wondering what do you think about one versus
Yeah.
eight in terms of proprioceptive prediction noise in that
Yeah,
sense?
that's fascinating. I think that would be yeah, because I don't want the manipulation to be purely a visual thing, right? I kind of want it to kind of manipulate it like in other ways, and yeah, number of targets might. I would think that more targets and this might be contrary to what you're finding. I would have thought more targets means you're more uncertain about where you moved because now it's not you're just not feeling the same direction. You're kind of, a little bit more uncertain about where you moved and where the target is. So I would predict that based on this model that more targets actually means less asymptote. So if we did an eight target experiment, we would adapt less than a one target experiment. So using the clamp feedback task. So that would be my prediction if it were a manipulation of prediction noise. But along those lines, there's another idea too, which is I was playing with the idea of introducing a block before during the baseline phase to make people feel like they're not moving to where they want to be. So if you reach to the target and I introduce like feedback that's perturbed left and right, just kind of randomly making people feel like their motor noise is greater, versus a case where, I kind of make people feel like their motor noise is smaller than it actually is. Maybe that's a way to manipulate this variable as well.
Yeah, no, cool. Yeah, glad that. Interesting that you say that because I've played around with, I think, similar stuff that you and maybe Tianhe did, where we sort of jitter the clamp error feedback a bit. So we introduce a 15 degrees clamp with a 4 degrees standard deviation jitter, and that seemed to make people adapt a lot more than when they don't have a jitter kind of
Oh
thing.
yeah. Yeah,
Yeah.
that'd be cool. That'd be cool. Yeah, we can talk offline about
Yeah.
that for sure. Tim, do you have a question?
Yeah, just had a quick so maybe following on from Eugene's idea is, I mean, I'm sure you'll find that different directions of motion and different parts of space will have different proprioceptive sensitivities and reliabilities. So you could probably just look at different workspace locations maybe as a way to get at that.
Yeah, no, that's a great idea. And actually, we are looking into that right now. I can email you and share with you some of the results there. We adapt less when we reach in cardinal directions. So if you reach to a cardinal direction, your proprioceptive noise is less. I think people are more clear, like, oh, they know where they move when they go cardinal, and they adapt less. And when they move diagonal directions, they adapt more. And so we have that empirical finding, but connecting the dots to Primo we haven't done that yet. Um, but interestingly, yeah, so that's implicit adaptation, but explicit strategies like the cognitive process, you're way better at cardinal because you can see a clear reference point and maybe you're adapting more. So there's kind of this interesting different effect on each system depending on target location.
Cool. And I know
Yeah.
you're going to have to keep moving, and I don't want to, it's a long question, so maybe we can take it offline. But I guess one thing I'm still interested in is obviously I'm really convinced that proprioceptive is important in these type of adaptations, but there's also multiple different forms in which you can model that. So any different way, like any particular evidence that you think this particular form is is the correct one versus some of the other ideas that have been proposed about how we incorporate it. So, I mean, it's probably too long to interrupt your talk now, but I guess just another thing that I've been thinking about. So,
Yeah, no, that's great. I think short answer is I don't think the form right now is the correct one. The one we proposed in 2022 is a bit outdated. I think Kunling Wei has some better formulations. The general principle is the same.
yeah,
There's these elements, but yeah, I think he formulated it a bit more better, in my opinion. Yeah. So
yeah. Well, I mean, all models are a bit wrong, so we'll.
yeah, completely. Um, so yeah, okay, I'll continue. So what are the neural correlates of adaptation? And I think it won't be that surprising, but I'm gonna go into the cerebellum because that's kind of a key element, key place we've been looking into. And let's just take a moment to marvel at the cerebellum. It's like a beautiful structure, 80% of the neurons in your brain. But oftentimes, you do animal physiology studies, oftentimes like dissected, removed, and not really investigated. So there's a surge of interest in the cerebellum right now, especially not just action, but also cognition. Of course, early days of cerebellum work, and fun fact that I didn't know about until I was doing some research on this was that a lot of the research was first done because there's been a lot of gunshot wounds to people, soldiers, and in the cerebellum because the helmet did not adequately protect the cerebellum. And because of that, neurologist Holmes at the time had observed that these patients with gunshot wounds to the cerebellum had ataxia, this under and overshooting of movement. And this is Rich Ivory, by the way, back in the day. So that's him. I love this video. So this under and overshooting of movement, and the idea has been proposed. Oops, sorry. And the idea has been proposed that these patients are generating the cerebellum is generating sensory predictions, and because you lose this prediction ability, people are relying on slow feedback signals, and so they're always a bit behind in correcting for their errors. So how does that idea manifest here? So we also find that cerebellar patients, a lot of work over the years, cerebellar patients adapt less than controls. What we contributed thus far, actually, more recently, is we actually did a meta-analysis on this, and it hasn't been published yet. But there's been 42 experiments we did, and like the effect size is just so robust, right? But we're actually identifying some gaps. I'll be happy to talk to you about that, maybe if there's time. But this reduction in adaptation does jive with Primo because we talked about a lot of perturbations or like manipulations we could introduce in healthy controls. But cerebellar degeneration, if it is doing sensory predictions, you're relying less on this ability, this signal that you reach to the target, this prediction that you reach to the target, and you rely more on proprioception. So you need to adapt less in order to feel like you're realigned back to the target. And so Primo might explain why cerebellar patients adapt less than controls. And the visual centric model has really no term involved in sensory prediction. And some other models that are more visual centric actually predict the opposite, that greater sensory prediction would drive enhanced adaptation. So I think it's a clarification that sensory prediction might reduce greater noise in this factor would reduce adaptation, just like what we observe in cerebellar patients. So Primo provides a specific account for the cerebellum's role in adaptation, and it predicts reduced adaptation like what we've been observing a lot in the literature. But how about the cerebellum's role in cognition? So as a motor learning person, like many of you, cognition was not my, uh, I'll speak for myself. Cognition was not my I wasn't really embedded in the literature until I was interested in the cerebellum. And I thought I've been reading this literature on how the cerebellum not only connects with motor cortex, but also prefrontal cortex, anatomically speaking. The cerebellum basically activates not just for motor tasks, but also for a whole slew of cognitive tasks. So what is it doing? And there's been a lot of work on this, but not a lot of work on how the cerebellum contributes to cognition. So there's been a lot of description, but we were interested in how we can develop a mechanistic account for how the cerebellum supports cognition. So we were inspired by the motor domain, similar to how we take a motor intent and generate a sensory prediction by simulating where your hand would be after you move and generating prediction to keep our actions well calibrated. Is the cerebellum doing something very similar for cognition, taking an intent of a decision, generating some simulation covertly, generating a prediction, and also keeping our decisions well calibrated? So we're extending this sensory prediction, this prediction error idea to the cognition. And so we wanted to test this. And we called this, we're calling it something different now, but we're still deciding on the term. At this time, we're calling it the mental simulation hypothesis. And it provides a falsifiable account for how the cerebellum might support cognition. So I'll provide some evidence for this idea, but I'll turn it back to motor in a bit. This is a bit of a break from motor for a bit. Actually, no, it's not a super break, but there is a little bit of motor involved. So here, the first place we turn to is actually a bridge between motor and cognition, the explicit strategies we do when we learn new movements. And so I just a task that isolates the strategies that we do when we do motor learning is we use this delayed feedback task. So in this task, participants reach to the target and they get some feedback. But the critical part of this is we not only provide instructions to tell people to explore, we're actually telling people to explore, please explore, and bring the cursor to the target. But at the same time, we delayed the feedback by 2 seconds. And like many of you know, that kills the after effects, that kills the implicit and isolates the explicit process. Okay, so we delay the feedback. In order to do this task well, participants need to do some simulation. They need to quickly, covertly simulate different action outcome associations and then realize that, oh, okay, reaching 60 degrees in the opposite direction gets the cursor on the target. And this has been shown to be correlated with spatial cognition, with different sorts of cognitive tasks. So if the cerebellum were involved in mental simulation, then cerebellar degeneration would also disrupt this process of strategy re-aiming. And just as a short plug, there's different processes to strategies. So we recently published a review synthesizing a new theory for strategy to kind of move forward on the mechanism on this front. So we said strategies involve 3 Rs, not recycle or whatever the 3 Rs are for recycle, whatever, reuse, but it's reasoning, refinement, and retrieval. Okay, so those are the 3 Rs. I encourage you to check it out. But a lot of the mental simulation process is happening in the reasoning part. Like, what is this spatial relationship between my movement and this cursor? So we predicted that the deficit would really occur in this discovery, this reasoning phase. So when we tested patients and controls were able to quickly discover 60-degree solution. They were able to quickly find out that they need to reach opposite, 60 degrees. But patients with cerebellar degeneration in this reasoning phase show a deficit. And both groups don't show any after effects, suggesting that this delayed feedback task isolates strategy. When we tell people to stop re-aiming, reach back to the target, no after effects. And during this retrieval phase, after they learned, and we say, please just show us again what you learned, both groups are able to do this very well. So this selective effect of the cerebellum being involved in the reasoning phase and not this retrieval phase provides some initial evidence that the cerebellum might be involved in this simulation process, not in simply retrieving a memory. But this task is still preliminary data. It's still like this, you might be arguing that this is easy, this is harder, this is easier, and there's still movement involved. So maybe it's just about movement, maybe it's just about difficulty, so on and so forth. So we went to a classic task where we minimized movement. We kept it, more cognitive, and this seems to be the cognitive process that is involved in strategy, and that's mental rotation. So the task is very simple. Judge whether the letter you see is normal or reversed. And the classic finding when you rotate this letter in multiple directions is that response time increases with the size of the rotation, as if people are covertly rotating this letter back to its upright position and making the judgment. And the slope of this function is the rate of simulation, the rate in which you're able to simulate this letter in your mind. So if the cerebellum were involved in mental simulation, then we would predict that patients with cerebellar degeneration would show a steeper reaction time slope because it takes them longer to make each rotation in their mind. And again, this task we chose this because it's a simple button pressing task. There's not a lot of motor demands in this task. So what do we find? We found that in two experiments, I'm showing you one, is that patients with cerebellar degeneration, they show an intercept effect, so they are slower. They are patients with movement disorders. But more important to us is that the slope of this function is elevated, suggesting that mental simulation in this mental rotation task might be impaired. But we needed a control task that's about equal comparable difficulty. So we chose a task that is about memory retrieval, memory recall, so less simulation involved. You're asked to remember the position of two dots, one and two, and you're probed on one of them, and you're asked, is this the first dot, the second dot, the fourth dot, the fifth dot, so on and so forth. So you can see that again, patients show a elevated reaction time just in general because they're slower, they're patients. But the slope, which indexes the rate in which you're retrieving things in memory, is no different compared to controls in patients. So this dissociation with a selective increase in slope in the mental rotation, not the memory recall, again supports the idea that the cerebellum might be selectively playing a role in simulation, not recall. So we went in a more, and lastly, we took this in a radical direction that I did not anticipate my education to take me back to, actually, because I studied math. But math apparently is a field that also relies a lot on mental simulation, ideas of mental simulation. So there's this idea of a mental number line. And so when you're learning math, and even when you're pretty good at math, when you do addition, like 8 plus 9 is 17, people still rely on spatial representations in the brain, and as if you anchor yourself at a number and you're like moving along this number line. And so this is a area of research, numerical cognition, that suggests that, doing math, even simple math tasks, does tap into mental simulation. And some evidence for this is like reaction time again scales with the amount you have to add. So if you add more numbers, larger numbers, you have to move more on the number line, so reaction time increases. And again, here we would predict that cerebellar patients would show a elevated reaction time slope because they have disrupted mental simulation abilities. And to our surprise, that was actually what we found. So compared to controls, patients who are doing this simple addition verification task, they're asked to, verify is this true or false, showed an elevated slope compared to controls. But in contrast, in a very similar control task, where they're simply asked to multiply, and usually multiplication relies more on recall because that's the way we learn it in a multiplication table. Um, in this task, patients and controls don't show a difference in the slope of the reaction time. So again, the selective impairment in the slope in the addition, not the multiplication, points to this idea that the cerebellum might play a selective role in tasks that are more algorithmic, more simulation based, not just simply retrieval from memory. And so this idea like simulation prediction, we can see a thread of that from the motor world and also in the cognitive world. And delineating this from recall, which might be more hippocampus dependent, not cerebellar dependent. So we think this is important because there's a lot of work coming out that's like cerebellum does everything, but it's important to draw constraints around what the cerebellum isn't doing, and that's how we can probably get closer to what the cerebellum is doing. I'll pause here to see if there's any questions on section 2.
Maybe I could just ask about particularly the delayed feedback reaching kind of work. And one thing that becomes really important, I think, when you're thinking about, is it simulation or is it um, something else, I suppose, is instructions that you give. So, um, what did you actually tell the people that their task was there? So, when we give people instructions on how to solve something and do explicit learning, often their adaptation is really fast, like immediate. And we can vary that depending on how detailed or exactly what we tell them to do. So, yours seemed reasonably gradual. So, I'm just curious about, I mean, what they have the opportunity to discover and explore, and then they have to, that's what that delay process is, you think?
Yeah, so let me show you some supplemental slides. So I would just note that our instructions are vague because we don't want to give them any idea of what the nature of the perturbation is, which is a rotation. We didn't want to convey that. We also didn't want to convey the size. So we didn't want to say 60 degrees. So what we just said is your goal is to get the cursor on the target. The cursor is doing something weird, and you have to explore different movements in order to get the cursor on the target. So we make the goal, the cursor on the target, very clear. Everything else, we keep it fairly vague. And, this innocent looking little learning curve, we're actually finding a lot of cool ways to try to dissect it, especially important for explicit. And just for you guys, because I think you guys might be interested in this. Uh, Even Primo, all the models that we talked about so far are models of gradient descent, right? They're like reduce the error gradually. But if you look at the individual data, especially in the delayed feedback tasks or tasks that are more explicit in nature that you see these curves, right? And we tend to average them. And if you fit the group average, it looks pretty nice. It looks, gradual. But if you look at the individuals, they look erratic. And so it's not a really great fit on the individuals. And this is actually called the ecological fallacy, assuming the group average represents the individuals. But sometimes the group average does not represent the individuals. So we thought, okay, what might be a better model for explicit strategies? And this is the work of Anjali Niyogi, and she's going to be a PhD student next year in the lab, and really excited to explore this direction. She has come up with a hypothesis testing model, and the general intuition is that people are not doing gradient descent towards like 60 degrees or whatever the error size is. People are actually exploring different ideas about what the perturbation is. So is it a rotation? Is it a translation? Is it a mirror reflection? Is it, zero? Is it 180? And people might come up with really creative ideas about what it is, right? That we are not even capturing. Is it clockwise, counterclockwise? And then they choose an action based on their beliefs about the nature of the perturbation, about the size. They observe the feedback, and then the cycle iterates, and they update their beliefs. So this system can generate errors that are more similar to what people are producing. And so it's more erratic. And so, yeah, so this is just showing that it can capture the between subject variability and also the errors that people are making, and they can be very bimodal.
Right.
Yeah.
Thank you.
Yep. Um, yeah, so the gradual part is kind of an averaging effect of a lot of exploration. Yeah.
Yeah. I mean, although we see it like in certain sequences, we see like the whole group gets there straight away, and there's very little variability. So just depending
Oh,
on
yeah,
what
yeah.
you,
Yeah, I think one thing we're realizing is, I don't know how many targets you have, but if it's a rotation, if it's like multiple targets, it does slow down the learning a bit because you really have to get this rotation rule. But if it's like one target, two targets in the same hemisphere, then people could come up with these interesting rules that are consistent with the solution, but not really the rotation specific idea. Yeah. So. So we're actually looking at a lot of this because there's a lot of individual variability. Online data gives us a rich way to tap into that. And I'm not saying that online data is the way to replace in-person data. It's a way to complement it. So typically we do studies with 20 people in the lab, has been great. And I've been reading a lot of papers from this group too, because I've been doing a lot of meta-analyses trying to synthesize the effect of dominant hand on adaptation, the effect of transfer, interlimb transfer, which I know a lot of you have done, and quantifying that. So, but a lot of our hypotheses is harder to test with 20. For example, left-handers. Like it's hard to find 20 left-handers really if you want to do a study like that. But online, you have this kind of new tool to study this in a lot of people. So it's open. You can design this experiment very quickly online. And so the first idea was to replicate in-person findings. So we did a experiment where we were just 45-degree rotation. People adapted a learning curve very similar to what you see in the lab. And when we ask people to stop aiming, they still show an after effect. So note that this is a computer and you can see your hand, right? And we were worried that people won't show any after effects because they can see their hand. But people don't really look at their hand. And even if they did, I don't think they would recognize what a 15-degree deviation is compared to where they were moving. So people do show an after effect. And when people came back for more, we replicated the classic effect of savings, right? That I know Leon has done a lot of work on. You adapt faster, but interestingly, you show less after effect. And that's some of the work Guy Avraham has been seeing in the lab. So we replicated that. There's this idea of contextual interference. You adapt faster with one target, but show less after effects. And two targets, you adapt slower, but show more after effects. So these findings we see online. So we were encouraged that we replicated some classic effects online. The noise is more, so anticipate that, but we double the sample than typical what we do in person. One other advantage of online tasks is we can benchmark human performance. So one example of this, and this goes back to Raphael's point about aging and what some therapeutic implications we're trying to make. And we took our online data set and we had around 2,000 people and we combined it with in-person studies. And we try to benchmark, for example, things like reaction time over age. Like how much slower do you get per year? And that hasn't been clearly answered with a few people in the lab. But interestingly, across all these data sets with over like 2,000, 3,000 people, it's a 1 millisecond decrease per year. We're able to quantify that and have some error bars around that. And that might not seem like much, but 20 to 80, 60 years, 60 times 60 milliseconds, that could be a difference between reacting to a car and dodging it. So it could build up. And there's movement time differences too, 2.5 milliseconds, and movement precision, and that's your motor noise during baseline. So these might serve as some benchmark data for future studies on aging. And one unappreciated way of using this that I haven't really thought about until someone brought it to my attention was if you want to quantify the intercept effect of patient and controls, you see like effects of the intercept, right? They're slower. But how much of that is just due to maybe aging? Some of this data might be able to inform that question. Like maybe 200 milliseconds is just due to aging, but the rest is really some other thing. So this is what large data sets might provide. We did a machine learning approach just to find what are some predictors of strategy. So what are the things that correlate with the late adaptation phase, but not the after effect phase. So interestingly, your visual ability. So this was with this large data set. We just asked people a lot of questions basically, and we just threw it all in a machine learning model. Your visual ability seemed to relate to your late adaptation, but not your after effects. How much, and this is interesting to me, but it might be weird to you, but like if you left the experiment and saying you loved the experiment, that was 5 out of 5, you adapted more than someone who hated the experiment. That this was a 1-star rating, but no difference in the after effects. So your after effects don't care about how much you enjoyed the experiment, but maybe, the late adaptation phase, your performance does relate. Um, and we don't really ask people in the lab if they enjoyed the experiment. But maybe that's a predictor of how well they did, which kind of makes sense. But who knows if it's motivation predicting performance or performance kind of suggesting that you enjoyed the experiment. But anyhow, I thought it was a cute finding. There are gender sex differences that we're exploring and could be due to video game use, different confounders that are not accounted for. So that's explicit strategies. How about implicit adaptation? The more variably you move during baseline, you adapted less. So this informs maybe some correlations that people like Maurice Smith have been asking about, your motor noise and how it relates to motor learning. I'll skip this one for now. But this one was to your point, Tim, was about direction of movement, and we typically average target location, right? We're like, three targets, we don't really care, we just want the workspace effects. But if each person in our study only reached to one target because our experiment was 8 minutes. So we could look at these effects of target location. And this was the biggest effect in our study. So people with moved to diagonal targets adapted implicitly a lot more than cardinal. And this might be due to the proprioceptive noise effect when you're kind of in these diagonal locations. You might be less certain about where you moved. So Anjali took the idea, the delayed feedback task, and did some modifications. And large online data sets allow us to answer some questions that are very difficult to answer in person without the scale of online studies. So she asked a question about what transformations are easy and what are hard. Because in real life, you experience things like gain, right? Like I don't know, your steering wheel, there's a gain to the wheel. You might experience mirror reflection when you use the mirror. What's hard? What's easy? So she just wanted to do an empirical ranking of this. And she found that she found that gain is super easy and rotation is surprisingly harder than some mirror reflection. So this is a cardinal mirror reflection, like vertical and horizontal is actually easier than rotation. But when you combine gain and mirror reflection, the two easiest, you become hard. Kind of makes sense. You make it hard. But the hardest thing here, I love to do this demo in person when I give this talk is a diagonal mirror. So you have to figure out that the perturbation is actually a reflection across this mirror. And that's really hard for people. So if you guys are looking for a hard perturbation to subject people to, diagonal mirrors is your friend. So we get this ranking, and that implies, that might give us some predictions about what are easy things to learn and what are hard things to learn in a motor learning context. And every group here has around 100 participants. So this study had 500 participants. So another question that's a little hard to answer in person is about handedness and hand dominance. So as you know, that 10% of us are left-handed, and it's hard to find people who are left-handed and do a study. And we took this motor learning task that's been very popular for a long time, rotary pursuit, right? Follow the dot. And we designed an online version of it, just like follow this dot, very simple. And we asked, how does this vary across handedness and hand dominance? And what we found was that right-handers have a big dominance effect. So I'm guessing most of us are right-handers. We're really bad at using our left hand. That's this bigger error for right-handers. But left-handers are sandwiched in between. There's a cost to their dominant hand, and there's a benefit to their non-dominant hand. So they're kind of ambidextrous. And what I'm noting here is also that the left-handers that we recruited were reporting 100% left-hander on the Edinburgh handedness scale. So they're not preferentially ambidextrous. They're preferentially left-handed. But motor performance-wise, they're ambidextrous. And this is not just a speed accuracy trade-off, because across all these speeds, the left-handers are all sandwiched in between the right-handers. So the right-handers show a big dominance effect. Left-handers are basically ambidextrous, despite them reporting that they're 100% preferring their left hand. So this is a dissociation between preference and performance, especially in the left-handers. So I added this slide because I know some people in this group are looking at intermanual transfer. And we're doing a meta-analysis, and we're finding that, first of all, there's two findings here. One is we did this online, asking whether dominance and handedness have any effect on motor adaptation and transfer. First is that we confirmed that people are better using their dominant hand. So we had two groups, one group that learned with their dominant hand, one group with their non-dominant hand. So in both groups, they're better at using their dominant hand. measured by how many clicks they can do to a grid of dots in a minute. So that's good. People are better at using their dominant hand. But they don't show any differences in adaptation, which is a bit surprising to us. There's some mixed findings in the literature, but hopefully with our sample sizes of 100 per group, we were clearly showing that there's no difference in terms of handedness. If anything, non-dominant is a little slightly greater than dominant. But here is the phase where you transfer. So both groups are able to transfer to their other hand equally well. And the amount of transfer is around a little less than 50%. So this data set tries to answer the question of there's no difference in dominant hand advantage and adaptation. And two is that implicit adaptation does transfer to the other hand around 40 to 50%. And I think, and correct me if I'm wrong, especially this group, you guys probably know more a little bit about this transfer effect, but I was actually under the impression that only explicit strategies transfer to the other hand, and implicit is like sometimes yes, sometimes no. So I was quite surprised to see that implicit adaptation did transfer pretty robustly to the other hand as well.
So one thing that I think is very important when you're talking about transfer is the reference frame that you're talking about. So we've shown that if you align the reference frames, then you get very, very strong transfer, and I suspect that's implicit as well. So obviously you've got left and right hand, it's more leftward or more rightward, but it's also more inward to the body, outward to the body, and those things conflict with each other. So if you can align the reference frames, you generally get very strong transfer. So
Yeah. So I remember some papers that I think you and Eugene may have had with the screen kind of on the side and in the front. Yeah. So in this case, it was kind of a computer setup. Their screen was here, and they adapted to a rotation of like a clamp feedback of I think 15 degrees. So in this case, they're adapting kind of rotationally, and they're transferring also in the same direction of the rotation. Sorry.
yeah, so that'll be the same direction in extrinsic coordinates, but an opposite direction in intrinsic coordinates of the
Yeah,
lens. So yeah, but I
exactly.
mean,
Cool. Yeah. So
That-
yeah, we didn't test.
So just a
Sorry.
comment as well. I think this also addresses some of the uh, dynamic hemispheric dominance that Bob Steinberg proposed a few years ago as well. Like I think he proposed that some parameters you would transfer better from non-dominant to dominant, and then others would be non-dominant to non-dominant would be better. And I think in your case, I think in this particular task, it seems to be equally well transferred across both hands. So I think
Yeah.
that also addresses that issue too.
Yeah. I agree, Eugene. Yeah. So yeah, we've been looking at that literature and yeah, so in this case too, the final learning is very comparable between two hands. So that makes the transfer part a bit more easy to interpret too, because there's like, the same amount of learning and now you're transferring both hands is also very similar. So yeah, and I think the dynamic dominance idea, I asked Bob actually, and also Nick Kitchen, who works in his lab, is which hand would adapt more based on his hypothesis. And they said that they actually thought that the dominant hand would adapt more because it's involved in feed forward movements, and this is a feed forward task. So, but that's not what we're seeing. So it could be, because our online setup, or we need to verify this in person in the future. Yep. So that's adaptation and transfer. And actually, can I ask clarification, Tim? When you said reference frame, uh, s- I guess, are you predicting that if we somehow align the reference frame, we can boost this transfer even more? That's what you're saying.
yeah,
You're not.
yeah, we've shown that in rotations, but also force field as well. If you align them, you increase the transfer. The basic idea is that whatever goes on in the brain to allow the recalibration, it may have a component which is related to the world and may have a component which is related to your body. So if those two things are opposite, then you're likely to see less of an outcome.
Got it. Okay, great. Sounds good. Okay, so and we did a meta-analysis in we're trying to quantify the amount of transfer, and that would vary, I guess, with the setup, and reference frame was something that I think we should take into account. Um, I'll wrap up with just a few more slides. So another is questions that relate to longitudinal studies that might get closer to real life motor learning. That's not just 1 or 2 hours, but 100 days. So collaborated with state space labs. It's interesting. Their state space has nothing to do with state space models, but David Heger's company where they have an app where they looked at people playing video games. And they I don't know if any of you play video games, but people want to get better at shooting on using their computer. And so they go to this app and they practice their shooting skills for free. So that gives them a lot of data. So that gave them 100 days of data and even more years of data. And you can see how motor skills, like how many hits per second develop over time. And so you can see that, people started out with around 2.8 and went up to almost 4 shots per second. And that's extremely fast. Like I can't even shoot one per second. This is super fast. So this is just a study where that exemplifies that gaming might be a way to study motor learning at scale. Lastly, one study that I'm really excited about that I was inspired by the movie Coda. Have any of you watched Coda? Child of Deaf Adults. And I was so inspired by how quickly people can sign. And I thought sign language was such a great motor skill that it involves sequence learning, involves motor execution, involves, what is the sign, involves language, emotion. Like it's almost like a great little paradigm to study motor learning in a real world scenario. So we thought, okay, can we design a task that studies sign language and use that as a way to understand the motor system and its interaction with cognition? So we designed a game in collaboration with some game designers actually at CMU, and we were about to launch this online. Right now it's still in person, but it's just a webcam task, and with any webcam doesn't need any special setup. You just have to learn the alphabets of ASL, American Sign Language. So that it's K, so you have to hold up the sign for K in front of the camera. It detects you, it pops the balloon and moving. So we get to collect all this interesting data with the hand, and there's like 50 landmarks, how they move over time. This is a lot of rich data, and the task is also in a format where it's easy to analyze. So we first just said, okay, does it distinguish between novices and experts? Because if it can't, then we're pretty screwed. So when people came in and during baseline, you can see that experts out of the 24 letters actually, because we removed 2 of them because they were kind of movement related. That was a bit complicated. People were pretty good experts are pretty good. Novices can guess 5 out of 24 correct. And so if I said, do the sign for C, you would do this. Even though you don't know ASL, you would have guessed 1 out of 24 correct. Um, so, and after just 30 minutes of intervention of kind of teaching you ASL, novices can learn up to almost 80% of the letters. And ASL letters are quite important for signing, so that's encouraging. But the experts tell us a bit about how our algorithm is not perfect. Experts should be around 24, even at baseline, so we're still kind of fine-tuning the algorithm to make it even better. And lastly, here we're trying to examine what signs are easy, what signs are hard, and that will give us clues about what's biomechanically maybe harder than others. So you have things like C and Y that are very easy for people, but then things like K is very hard. Things like P is also hard. So this might give us some insight about like dexterity and what are some difficult dexterous movements. Maybe they don't occur in life as often, and we can hypothesize about that. So yeah, sign language, especially in the online context, we think we can kind of understand a lot about dexterity. So to wrap up this last section, large-scale crowdsourcing, of course, is not the replacing in person, but it gives us some ways to tackle some questions that may have been a bit hard to tackle in the lab and give us some cool pilot data for them to test in the lab. So with that, those are the three sections I covered today: mechanisms of motor learning, the cerebellum's role in cognition and action, and also methodologically the power of using online data. And why is this important? So we come back to our main question of how do humans acquire, adapt, and retain motor skills? All this is important because, I'm a motor chauvinist, as Wolper would put it, because I think motor learning can give us clues into learning and memory in general that's very observable. And of course, helping us design brain-computer interfaces, like should we listen to S1 more? Should we listen to M1? And what are the signals telling us? How do we train people to use these brain-machine interfaces in the future? And of course, to optimize human performance. And what I'm really excited about is to take the ASL work that I'm doing in the future to maybe work with the deaf and hard of hearing community to see if any of these insights can be applied to helping people learn and accelerate their ASL learning. So with that, I'd love to thank the lab and thank the people that did a lot of this work. And we're still growing, and we'd love to have any of you visit anytime if you come by Pittsburgh. And thank you so much for your attention.
Thank you so much, Jonathan. That was fantastic.